have discussed about lime soda process, and in this lecture we will discuss about zeolite process of softening of water. Now, as I have told you in the previous lecture, that the water which is used in industry, that should be pure from all types of temporary hardness or permanent hardness, like presence of calcium ions or magnesium ions or iron ions in the form of their salts. Otherwise what will happen, that our boilers, they will become ineffective in their operation due to formation of scale and sludge, and even the presence of these ions that can cause corrosion in those boilers. So therefore it is of utmost importance that the industrial water which we use, that should be free from all types of salts which cause hardness in the water. Now, the process of removing these hardness producing salts is known as softening of water. And as I have told you in the last lecture, that these are the four common methods which are used for softening of water. In the last lecture we have discussed about lime soda process, that how different types of lime soda processes, like cold water lime soda process or hot water lime soda process, can remove temporary or permanent hardness in the water which is to be used in industry. And then I have told you about the various reactions which take place with lime and soda of these salts which cause hardness. In the present lecture, we will discuss mainly about zeolite or permutoid process. The zeolite process or permutoid process, this has come from the Greek word "zein boiling," which means the boiling stone. This term was used in 1956 for some group of naturally occurring materials which released their water of hydration in the form of steam. So from this boiling stone, this word permutate or zeolite has come, and the most common example of such naturally occurring raw materials is hydrated sodium aluminosilicate, or this is commonly called as sodium zeolite. The chemical structure of sodium zeolite is that this is having two sodium ions in the form of Na2O, then one molecule of aluminum oxide Al2O3, then X molecules of silicon dioxide SiO2, and Y molecules of water. And this X may range from 2 to 10, whereas this Y may range from 2 to 6. So depending upon the number of X and Y, the nomenclature of these zeolites is done. So all sodium zeolites, they can have silicon dioxide molecules ranging from 2 to 10, and water molecules, water of hydration ranging from 2 to 6. Then this sodium zeolite, what it does to the hard water is that we know in the hard water there are calcium ions and magnesium ions. So those calcium and magnesium ions, they can be reversibly switched with these sodium ions. So what will happen? This sodium will go to the hard water, and calcium and magnesium ions, they will get attached at this place, and the sodium zeolite will be converted to either calcium zeolite or magnesium zeolite, whereas calcium bicarbonate or magnesium bicarbonate, that will be converted into sodium bicarbonate. So this is how sodium ions, they are reversibly switched for the hardness producing ions in water. Now zeolites or permutites, they are of two types, either natural zeolites or synthetic zeolites. The natural zeolites, they are non-porous in nature, and they are very tough, and they are derived from green sands, and they can be prepared from green sands when these sands they are first washed, then heated, and in presence of caustic soda. So if we heat these in presence of sodium hydroxide after washing, then these will be converted into the natural zeolites, which are non-porous in nature. And most common and important example of natural sodium zeolite is natrolite. So this is most common, where the value of this X is 4 and Y is 2. There are 2 waters of hydration and 4 silicon dioxide molecules in this zeolite. So this is most commonly used in the zeolite process. Then second category is synthetic zeolites, and these are porous in nature, and they have gel-like structure. Then synthetic zeolites, they can be prepared by heating together with the china clay, feldspar and soda ash. When all these three they are heated together, we will get a product which will be known as synthetic zeolites. And these synthetic zeolites, they have higher exchange capacity per unit weight than the natural zeolites. So they have higher exchange capacity per unit weight than the natural zeolites. Now, theory of this zeolite process is, as I have told you, that sodium ions which are loosely bound to the zeolite moiety, they can be easily replaced by calcium and magnesium ions which are present in the hard water. So when hard water containing these dissolved sodium and magnesium salt is passed over a bed of sodium zeolite, then these ions they are replaced with sodium. So these are the reaction how this takes place. For example, if we are having magnesium bicarbonate salt dissolved in water, so what will happen that the bed of sodium zeolite will interact with this magnesium bicarbonate, and this sodium ion in the zeolite will be replaced by magnesium, and this will become magnesium zeolite, and magnesium bicarbonate will become sodium bicarbonate. Similarly, if there is present calcium bicarbonate, which is responsible for temporary hardness along with magnesium bicarbonate. So here calcium will be replaced by sodium. So we will get calcium zeolite and sodium bicarbonate. So these are the two responsible for temporary hardness. Then these two, they are responsible for permanent hardness. We know the permanent hardness is because of chlorides and sulfates of magnesium and calcium. So if in the hard water we are having magnesium chloride or magnesium sulfate, that will react with sodium zeolite, and we will get magnesium zeolite, and either sodium chloride is formed if magnesium chloride is present, and if magnesium sulfate is present, sodium sulfate. Similarly, if we are having calcium chloride or calcium sulfate, then this sodium will be replaced by calcium. We will get calcium zeolite, sodium chloride or sodium sulfate will be formed if in the dissolved water we are having calcium sulfate or calcium chloride. So this is how the temporary hardness or permanent hardness is replaced by the sodium zeolites. Now, as I have told you that sodium zeolite is transformed into calcium and magnesium zeolite, whereas water will become free from these ions, calcium and magnesium ions, and therefore this will become better in terms of hardness for sodium salts. So therefore zeolite here is acting mainly as sodium ion exchanger. And then these are the zeolite which are formed after softening of water. These are called as exhausted zeolites because now they have no capacity to replace sodium ions, but these can be regenerated or these can be transformed again into sodium zeolite and they can be reused also. So if we treat these with brine or sodium chloride solution, then this calcium zeolite will be converted into calcium chloride and sodium zeolite will be regenerated. Similarly, if we are having magnesium zeolite, when this reacts with sodium chloride, we will get magnesium chloride and sodium zeolite will be regenerated. So this is how by washing with sodium chloride, the zeolites they can be redeveloped or regenerated to be used again for softening process. Then this process, how in actual the process takes place. So what happens is that hard water is added from the top over here, and through this injector we are adding the more water from this side, and this hard water passes through this geolite bed, and in this bed the calcium and magnesium ions of hard water they are exchanged with sodium ions. So uh, this will through gravel the soft water will be taken out from this outlet, and we will get our soft water containing sodium bicarbonate instead of calcium or magnesium bicarbonate. The limitation of this geolite process is there are quite a few limitations, because you have seen that only thing this geolite process is doing, that it is removing calcium or magnesium ions and to some extent iron and magnesium ions also. These ions are replaced in the hard water, but this is not effective against any other type of impurity. So furthermore, the zeolite process this becomes ineffective if the water which we are using is a dirty water, because dirty water will have suspended substances, and these suspended substances they will block the whole of the zeolite bed, and when whole of this geolite bed is blocked, then there is no possibility of exchange of sodium ions with the other ions. So our process becomes stationary. Then this process can also become ineffective if we are having a large amount of colored ion like magnesium ions or iron ions. These ions they will if these ions they are exchanged with sodium, that means we will get manganese zeolite or iron zeolite. So these manganese and iron zeolites they cannot be easily regenerated, so that is why our process will become ineffective. And third thing is that this process gives good result only with cold water. If we will use hot water, then results will not be good, because some of the sodium zeolite will get dissolved in water. So zeolites they tend to become soluble in hot water. So that is why we cannot use hot water. This process is effective only in cold water. Then you have seen that this process can exchange only cations, that is calcium ions and magnesium ions, they can be exchanged, and bicarbonate ions, they cannot be exchanged. Because bicarbonate ions, they cannot be exchanged, and these bicarbonate ions, they dissociate to give sodium hydroxide and carbon dioxide as byproducts. And both these sodium hydroxide and carbon dioxide, they affect the boilers in a big way, because this sodium hydroxide causes caustic embrittlement, and carbon dioxide that can cause corrosion in the boilers. So these are undesirable byproducts of softening process. So in this way also, there is a limitation as far as zeolite process is concerned. Then if in our hard water some mineral acids they are also present, then these zeolites, they also react with mineral acids, and we will get some byproduct, or we can say that the zeolite bed is demolished by mineral acids. So this process is not effective if in our hard water there are some mineral acids. Then there are some advantages also, and disadvantages are mainly the limitations which we have discussed. So advantages is that it removes hardness completely, and we can get a water up to 10 ppm hardness. And as second is that as no impurities they are precipitated, so there is no sludge formation. So that means we need not remove sludge from the process for getting the treated water. So this is another advantage, but then this can be treated as disadvantage also, that because those impurities we are to precipitate out by some other process. Then another advantage is that simple equipment is used which is compact, and the process automatically adjusts that how much of zeolite is to be used. So variation depending upon the variation in the hardness of the incoming water. So this is also an advantage over lime soda process. In the lime soda process, on the basis of amount of hardness, we have to calculate the amount of lime and soda and coagulant required, and then we are to add. Whereas here in this process, this is automatically adjusted that how much of zeolite is to be required for the process depending upon the hardness of incoming water. Then process is very clean. There are no side products, no sludge formation, no any other impurity is formed. So that is why this process is very good. Then it requires less time for softening, and it can remove iron and magnesium from water also, because those two ions they can also be exchanged. Then it requires less skill for maintenance as well as for operation of the process. The disadvantages, as I have told you, in limitations also, because the sodium ions are exchanged, though that means our soft water or treated water will contain more of sodium salts than we get in lime soda process. Then second disadvantage is that it replaces only calcium and magnesium ions by sodium ions, and not the acidic ions present in the soft water. And these acidic ions, as I have told you, they will produce byproducts like sodium hydroxide and carbon dioxide, and both of these they can cause either corrosion or caustic embitterment as the side product, which can cause damage of the equipment in industry. then high turbidity water cannot be treated efficiently by this method because impurities they will get deposit on the zeolite bed, and the process becomes ineffective. So this is the book which has been used for this lecture, Chemistry for Engineers by Harish Chopra and Anupama Parmar. This is published by Alpha Science UK, and the national edition of this book is available with Narosa New Delhi. Thank you very much for your patient hearing. Thank you.